Alright, welcome back. So, I had a quick scuffle with a friend, but let's try to get back here to what eigenvectors are for. And I think ChatGPT gave us a pretty good observation here. And the way we could use eigenvectors are to actually project our data onto something called principal components. So these principal components are represented as eigenvectors on our data set, and they kind of represent vectors in which the variance of the projection of our data onto those vectors is maximized. So I'm trying to think about this in terms of linear algebra stuff, right? Because the eigenvalue is kind of like the determinant in some sense. It's the scaling factor for so it's the factor at which we scale our, what do you call it? Our vector, right? And so if you were to scale our vector a lot, then you have a really high eigenvalue. And the eigenvalue itself represents the variance of the projected data onto our principal component. Disconnect is maybe a question I should ask ChatGPT. Let me think about this real quick. So, if we have a really high eigenvalue, right, that means we have a lot of variance along this new principal component. And that's the same thing as saying we scale our principal component by a really high amount. The eigenvalue we get comes from the covariance matrix. And a covariance matrix is a measure of covariances between different attributes or variables. I'm maybe having a hard of taking our covariance matrix and then our eigenvector, which in this case is a principal component. Let's think about that then. So we have in the first row of our covariance matrix the measurement of the covariance between the first feature and then also across all the other features. And we take a dot product with the first eigenvector. That's our principal component. And so we can think of each different value in the eigenvector as weights we scale the dimensions by. The dimensions here refer to the basis vectors or the variables in our data set. The dot product then between the covariances and then also the values that we scale each dimension, we have the variance multiplied by the value we scale the first dimension, covariance that you scale the second. So I'm not entirely sure how we actually interpret that number. Because that'll then give us a vector that I'm not entirely sure how to interpret that. Wait, so let's try to see this. How can you explain how the relation between the eigen eigenvalue and eigenvariance of the projection. Projected on the eigen. Let's call this principal component works. Good, so there's a lot to unpack here. Let's try to break this down. I think this is something actually kind of interesting here. The total variance of the original data is the sum of the variances of all original variables. The proportion of variance each principal component captures is calculated by dividing the eigenvalue associated with that component by the sum of all eigenvalues. So this is a bit confusing here. Let me try to read this. The proportion of the variance that each principal component captures, dividing the eigenvalue associated with the component by the sum of all. Okay, so that makes sense. Actually, this is just a proportion. Okay. Can you explain part 4 further? How is the eigenvalue the variance of the projected data? So the variance of the data when projected onto the eigenvector v is equal to lambda. This is derived from the properties. When you project x onto vi, the new coordinates zi for this projection are given by zi is equal to x vi. Okay. It's calculated as the average of the squared deviations from the mean. Okay, so maybe this is a critical assumption here that the data is centered actually with a mean of 0. Oh man, okay. So we have the variance of z is just equal to the sum of all z's. Because what we're doing is we're taking zi minus 0 squared. Okay, so this seems to be some type of critical equation here that we kind of have to understand, although it's not really clicking yet. So it's saying here that the definition covariance of the projected scores Yi with themselves is equal to the eigenvalue I, because the variance of the projected scores is equal to the variance of the transformation of x and Vi. And this is equal to Vi I forgot what exactly this represents, but I know this is pretty important. So, okay. I'm gonna copy this. What does this term mean? Oh shit. I think it got fucked up. Oh, nice. Eigenvector of the covariance matrix. So this is Vi transpose be n by 1 by n, then n by n yeah, this is tough. I'm gonna see if I can get some intuition from the StatQuest video that we saw. I'm gonna go into the small component analysis. Okay, so this is pretty helpful, and going back to the idea of how linear combinations form principal components. Okay, so this is the centering step. Okay, so I think this is probably pretty important actually. Why is minimizing the distance from the line of best fit the same as maximum distance from the projected. So the distance between the line of best fits, in this case, is B. Distance between the projected point to the origin is C. So if this is reduced, okay, so we have to increase C. Oh shit, okay. I think this is starting to make a little bit more geometric sense. Because in this picture, there's two things to think about, honestly maybe three. You have the distance from our projected point to the origin, which is C. Actually, let's start with A and then work our way across here, because I think that's a more intuitive way to understanding this. So you have a data point here, and then you have the distance between your data point and the origin. This should be constant because your data point never changes. It's always going to be there. For your observations. Let's assume that this isn't a time series observation. So your data point, once you observe it, it's going to be there. It's not going to change. So this stays constant. B here represents the distance from our data points and then also the principal component. Or maybe you could call this line of best fit. This is the line that minimizes the sum of squared residuals. The residual being this B here. And so this line tries to minimize this distance. And this line here is the distance from, if you were to project this point onto the line of best fit, distance from this projected point to the origin. And this quickly resembles a right triangle. And I don't know the proof for this, but we learned about this in middle school that the square root of both sides of these triangles is equal to the hypotenuse. So, in this case, if we're trying to minimize this distance, B, in order to preserve the laws of triangles, aka the Pythagorean theorem, we have to increase C. We increase C, I think, by shifting this point a bit closer maybe to right here, so at the end of this right angle. And so this will slightly increase the distance from the origin to our projected point. And that simultaneously decreases the distance from the projected point to our actual point, all while keeping A constant. And so when you hear people say that you're trying to minimize the sum of squared residuals, or the distance between the projected point and the actual data point, it's the same thing as maximizing the distance from the origin and the projected data point. All right. Maybe that provides some intuition about PCA. I'm still a bit confused here, and my screen has been frozen this whole time. So what I'm going to do is probably stop the stream for now. I gotta go to class in about 8 minutes and use the bathroom, so maybe I'll come up with some intuitive way to think about this, but I think this is kind of grounded in some complex math. It's going to take some time for me to understand. But thanks for tuning in, and catch you guys.